So for sample test 2, number 1, you're given a system of nonlinear differential equations, and you're asked to draw the phase portrait, find the equilibrium points, and investigate those equilibrium points using a linearized function. So let's find the equilibrium points first, and if a point is an equilibrium, then the x prime and the y prime both have to be equal to 0. So if you set these two equal to 0 and substitute into the system, what you essentially get is the first one would be x squared plus y squared equal to 10. That's just a circle with a radius square root of 10. So it's pretty easy to conceive what that is. Now, if you what that means is x prime will be 0 for every point on that circle. So let's look at the other one. That's just going to get you a parabola. If you substitute 0 in there, do a little rearranging, you would get y equals something like this: 7x squared plus 1 divided by 2. Okay, and that's just a parabola. So what that means is that on that whole parabola, y prime will be 0. So what you want to find is where they intersect, which is really, that's more of a pre-calculus thing. So I'm not going to go into how to do it here, but you solve for y, set them equal to each other, and what you get, this is what these two graphs would look like. So this turns out to be kind of a trivial solution. You find that over here, this point is 1, 3, okay? And if you know anything about graphing, you know that this parabola is symmetric about the y-axis, so is the circle, so the other intersection point you expect is -1, 3. Okay, so now you have the equilibrium points. Let's investigate whether they will be stable and what kind of equilibrium points they are. So to do that, we have a nonlinear system. We're going to linearize it using the Jacobian matrix and then investigate using eigenvalues. So clear the page here. So basically we need the Jacobian of our system. So here's our system of equations that we want to linearize, and here's how you get the Jacobian matrix. It's just a few simple partial derivatives. And the Jacobian matrix is going to allow you to find the linear system at some point x and y. I just said x naught, y naught here. Of course, we're going to investigate the equilibrium points. They're the most interesting. So it'll just be, and I've called the x prime equation f and the y prime g, so you can have partial of f with respect to x, partial of f with respect to y, then partial of g with respect to x, and partial of g with respect to y. So to carry this out is pretty straightforward. Partial of x with respect to y, in this case minus 2x, and then minus 2y. Sorry, those are separate entries. I'm just running out of space here. Then the bottom, you'd get minus 14x and just positive 2. Okay, and just pretend that that goes over and is our matrix. Ooh, that's a little ugly. That's okay. So now we're just going to make some simple linear systems with these using our equilibrium points. So let's see what J of 1, 3 would be. Okay, so that would give you a linearized system at the equilibrium point 1, 3. Substituting -1 in for x, you'd get negative 2 here and negative 14 down here. Right? Yep, and then for y, you should get negative 6 and 2. Okay. That is for one of them, and the other one is negative 1, 3. Right, so here, and I should really have equal signs here. You're going to get something like putting negative 1 in, I guess you get 2, and positive 14. Y is the same, so negative 6 and 2 over here. Okay, and now what you want to do is we're simply just going to find the eigenvalues of the system and use it to determine what kind of stationary points we have. And once we know that, it'll be pretty easy to make this phase portrait. So I'll just make some space here. So the first one, so let's find the eigenvalues of the matrix corresponding to 1, 3. So you would just get lambda squared minus the trace of the matrix, which is just the diagonals added together. So minus 2 plus 2, that's 0 times lambda. And then let's see, plus the determinant of the matrix, which is minus 40 or minus 4, minus 6 times 14, and that equals 0. So that's your characteristic equation. And I think this comes out to lambda squared minus 88 equals 0. So solving that, what would we get here? Just lambda plus root 88 times lambda minus root 88. Now, if you're on the test and you want to make Mijovic happy, maybe you should simplify that. But for this purpose, I don't really care. We just need to know what kind of roots they are. Those roots are both real. So we have no imaginary roots. So basically what that means is that we'll have a saddle. So this is a saddle point. Okay. And of course, a saddle is not stable. So you'll have at 1, 3, you'll have something, I don't know exactly what it looks like, but they'll be kind of doing something more or less like that. So you have a saddle point there. Let's look at the other one. I'm just going to delete this. Here, solving for that one, again, it'll be lambda squared minus the trace of the matrix, which in this case 2 plus 2 is 4, times lambda, and then plus the determinant of the matrix, which I think in this case is 4 plus 84, so plus 88, and that equals 0. So now if we find the roots of this to get our eigenvalues, just using quadratic formula, negative b plus or minus square root of 16 minus 4 times a, which is 1, times 88 over 2a. So again, I don't really care about simplifying all of this, but you can see that under the square root, you'll get a negative number. So and then what the number outside will be positive. So what do you get? 2 plus or minus square root of, I'm just going to be really lazy and say it's something negative in there. So what this tells you is you get an imaginary part and a real part. The real part is positive, so that means it's going to spiral out from this point. So this is going to be a source that spirals out. A source meaning that it starts. The equilibrium point is the source of this solution, and then it'll spiral out from there. So a source and spiral. And from that, you should be able to put together a pretty good phase portrait. And you can just pick the, what do you call it? Yeah, you can pick some just arbitrary x and y values and see what the slope will be, right? The x, and you can draw just little vectors and then add them. So, I don't know, for example, what x prime minus x squared minus y squared. I don't know, by this point, this is really pretty straightforward. Maybe it's not so interesting. Say, for example, at 0, 0, I wanted to see what this thing would look like. I just put in 0 for x and y, and you see the x dot is 10, the y dot is 1. So that means for the phase portrait, well, you'd kind of have an x that would be like 10, and a y that would be 1. Okay, and the scale might not be all that great, but that's going to be more or less a horizontal vector. So maybe if I was doing the phase portrait, at that point I would put something kind of like that. But you can do as many as you want of these. So that's more or less what you have to do to find the stationary points and determine whether they're stable or not. If you want a more thorough explanation of finding equilibrium points and Jacobian matrices, have a look at edx.org. And there's a differential equations course there. It's from Boston University, so do a search for something like, I don't know, BUX. I think it's 226.3. Maybe there's an X on there. So it's module 2. It's all about equilibrium points. So if you want more detail, have a look over there. And if you like this video, please subscribe to my YouTube channel, and in the future I'll probably make videos that might have quality even better than this one. And yeah, if you'd like me to make a video for something, feel free to ask. If I have time, I'd be glad to do it. Thanks for watching.